Welcome to this microlecture on simple and multivariate linear regression, part of the machine learning atom series. Today we will explore how linear regression helps us analyze and predict data relationships using statistical modeling. Linear regression is a method used to model the connection between one or more independent variables, known as predictors, and a dependent variable. It allows us to uncover patterns, make forecasts, and support decision making. Fundamentally, it's based on the assumption of a linear relationship between the variables, typically illustrated by the straight line. Simple linear regression means we only use one independent variable, typically noted as x. The goal is to estimate a linear dependence between x and outcome variable y, based on observed data. This relationship is usually expressed with the formula y equals b0 plus b1x, where b0 is intercept and b1 is the slope of the line. Even if we transform the predictor variable, for example by using logarithm on polynomials, as long as the parameters or coefficient enter the equation linearly, it's still considered linear regression. The goal of regression is to determine the line that fits the data most accurately. Best fitting refers to the line that minimizes the sum of the squared differences between the observed data points and the lines itself, and technique known as least square method. If the residual, that is, the gaps between the actual and predicted values, are large, it indicates a poor fit. To improve the model, we refine the line by reducing these residuals until we achieve the best possible fit. In this case, the line has smaller squared residuals, indicating that the model fits the data more accurately. In this example, we observe that layer thickness increases with time during an electroplating process. The regression equation tells us that the thickness grows about 0.83 microns per minute after initial delay of roughly 3 minutes. Real-world problems often involve more than one influencing factor. Multivariate regression allows us to model the relationship between a dependent variable and multiple predictors, whether continuous or categorical. It helps us assess the individual and combined effects of these variables, enabling more accurate predictors and informed decision making. As shown in the diagram, different values of predictors like x1 and x2 affect the outcome variable y in varying ways, which this model helps capture. In multivariate model, we estimate the intercept and a set of coefficients, one for each predictor variable. These coefficients tell us how the dependent variable changes in response to a one unit change in a specific predictor, while all other predictors are held constant. This relationship is shown in the formula displayed on this slide. In this equation, yi represents the predictor value of the dependent variable for observation I. In the term beta 0 is the intercept, which indicates the expected value of y when all predictors are 0. The coefficient beta 1 and beta k shows the effect of each independent variable x1 to xk. The final term epsilon represents the error or residual, capturing the variation in y that is not explained by the model. We use real data samples to estimate these coefficients. The intercept b0 tells us the expected value of the dependent variables when all predictors are 0. This is also known as the intersection with the y-axis, just like in simple regression. Each slope coefficient, such as b1, represents the net effect of the corresponding predictor variable. Specifically, b1 indicates how much y changes with the 1 unit increase in x1 while holding the effect of other variables like x2 constant. This slide illustrates a multivariate regression model with two predictors and one outcome. The plane shows how y change based on x1 and x2, with each slope representing the effect of one variable. Let's look at a real-world example, predicting apartment prices based on site and number of rooms. Multivariate regression helps quantify how much each factor contributes to the price. You can see two sets of regression results. The first table shows a simple regression using only the area, while the second includes both area and number of rooms. The improvement is clear. Adjusted R squared increased from 0.10 to 0.45, meaning the model explains much more of the price variation when both predictors are included. Also, the p-value shows that both variables are statistically significant, especially the number of rooms, which has a strong effect on price. To make useful prediction, our model must meet certain conditions, but more of that later. Assuming it does, we can estimate outcomes based on real inputs. In this case, using average values for size and number of rooms, the predicted apartment price is around 213 euros. If we increase the area and add 2 rooms, the model predicts a significant price increase. This shows how regression can be applied for practical forecasting. Let us now consider the coefficient of determination denoted as R squared or R2. This statistic indicates the proportion of variance in the independent variable y that can be explained by the set of independent variables included in the model. As displayed on the slide, R squared is calculated as a ratio of the regression sum of squares SSR to the total sum of squares SST. A value of R squared closer to 1 signifies a stronger explanatory power of the model. However, it is important to note that R squared tend to increase with the addition of more predictors, regardless of their relevance. To address this limitation, the adjusted R square is used. This adjusted measure accounts for the number of predictors in the model and increases only when the added variables contribute meaningfully to explanation of the dependent variable. We have retrieved the fundamental aspects of regression analysis, including simple and multivariate models. In the next presentation, titled Advanced Concept in Linear Regression, Assumptions, Dummy Variables and Interactions, we will explore these assumptions in greater depth and discuss how to handle categorical variables in interaction effects in a regression model. Thank you for your attention.